Okay, so now once again, welcome, and let me tell you what we are going to do today. We will finish our fuzzy reasoning examples, and then we might already continue with the topic how we can generate fuzzy sets in GIS. So let me first share my screen. Just one moment. Okay. So now you should see my spreadsheet again. Last time in class, we were discussing how to do fuzzy reasoning. And we were looking at two examples, or we were looking at two major methods. One, the direct method by Mamdani, and the simplified method. And you will recall that Mamdani's direct method produces as a result a fuzzy set, and we need to apply a defuzzification step at the end. For the simplified method, the rules, the conclusions of the rules are not fuzzy, therefore the procedure is somewhat simpler. Once again, when we were looking at the procedure for the simplified method, the Mamdani direct method, which looks like this. So you can see that there's a four-step process. And then we looked at the simplified method, which is just a three-step process. And we were working on one example. We were working on the example using the distance between cars and the speed and the acceleration with four rules. And we were doing that in an Excel spreadsheet using both Mamdani direct method and the simplified method, which you can see here. And after that class, I will make these spreadsheets available to you. So you have these examples and you can look at these examples, how it works, and you can use these examples as a template. Because today you will get another exercise where you will have to perform a fuzzy reasoning example using Excel, and you can use these examples that I will make available to you as a template. So I do not repeat all the details from last time. So that was Mamdani's direct method with this example. And then we did the same thing also with the simplified method. And what I'm going to do today is I will show you another example. Another example which I will mention here. So if you look at these rules, there are four rules about slope and aspect and risk. As you can see here, these rules are referring to the simplified method because the conclusion is not fuzzy. The conclusion is a number 1, 3, 1, and 5, which is a kind, in our example, which is an indication of the risk. So 1 is low risk and 5 is a high risk, and in between we have 1, 2, 3, 4, and then 5. So the rules are only as an example here. So I'm not a geomorphologist, so therefore I'm not pretty sure whether this makes sense in physical geography, but nevertheless, we use it as an example. And the rule number 1 would say, if the slope is flat and the aspect is favorable, then risk is 1. Rule number 2 says if the slope is steep and the aspect is favorable, then the risk is 3. Rule number 3, slope is flat and the aspect is unfavorable, then the risk is 1. And rule number 4 says if the slope is steep and the aspect is unfavorable, then the risk is 5. So what we want to do is we want to implement that again using an Excel spreadsheet with the simplified method. So what we need is, of course, we need fuzzy membership functions for flat and steep slope. In our example, I have defined flat slope in such a way that from a slope of 0 degrees up to 20, the membership decreases. So 0 degree slope is definitely flat, and from 20 on, it's definitely not flat anymore. And steep slope is defined in such a way that up to 5 degrees, it's definitely not steep. Then it increases up to 25, and from 25 on, it's definitely steep. Then we need fuzzy membership for favorable and unfavorable aspect. I define favorable aspect in such a way that I say from north to east, and you know that for example, the aspect is indicated in degrees from north. So 0 degree is north, 90 degrees is east, 180 degrees is south, 270 is west, and 360 is the same as 0 is north. So I define here from north to east, meaning from 0 to 90. It's definitely, sorry, I should look at the red line here. From north to east, it's definitely not favorable. Then it increases at 180 degrees, meaning at due south, it becomes 1. And then it decreases again until west, which is 270 degrees. And from there on, it stays 0, meaning definitely not favorable. And unfavorable I define as the complement of favorable, meaning 1 minus the membership values for favorable. And then we can look at slope and aspect values and see what the risk will be depending on which slope and which aspect. And in this particular example here, we have a slope equal 10 and aspect equal 180 degrees, meaning due south, that is 180. And what we would have to do is, again, we have to look at our rules. And our first rule says flat slope and favorable aspect. So we have to go with a slope value of 10 into the flat slope and an aspect value of 180 for the favorable aspect. So for a value of 10, we get here a value for flat slope of 0.5, and for the aspect with 180 to favorable aspect, we get a value of 1. And again, according to our procedure, for the direct method, we have to go with these given values into every rule and compute the minimum of the premises, the premise variables, so which in our case gives us for rule number 1, 0.5 and 1, where the minimum is 0.5. For rule number 2, the values are 0.2 and 1. The minimum, of course, is 0.2. And for rule number 3, it's 0.5 and 0. The minimum equals 0. And for rule number 4, it's 0.2 and 0. meaning that the minimum is 0. So that would be our first step. And again, when I go back to the procedure, so we just finished this first step here. Now we have to compute the conclusion values per rule by multiplying the corresponding minimum with the conclusion value. So in our case, the conclusion value is in the first rule 1, then 3, then 1, and then 5. So for the first rule, we have to multiply 0.5 with 1. Here we have to multiply 0.2 by 3, because the conclusion for rule number 2 was 3. And then for rule number 3, the conclusion value is 1, and for rule number 4, the conclusion value was 5. However, since the minimum was always 0, the result is also 0. And then we have to compute the final value, which is given as the sum of these conclusions divided by the sum of the minima. In our particular case here, the sum of the conclusions would be 0.5 plus 0.6 plus 0 plus 0 divided by 0.5 plus 0.2 plus 0 plus 0, which you can see here, giving a value of 1.57. So what does that mean? For a given slope of 10 and a given aspect of 180, with our 4 rules that we have defined, the risk value is 1.57. And in a similar way, you can compute that for different values of slope and aspect. And in fact, I have done this also in our spreadsheet here. So we have here our spreadsheet where we have the definition of the membership function for flat slope, for steep slope, favorable aspect, and unfavorable aspect. And we have implemented here these membership functions in a table in Excel. So for flat slope, we just implement our membership function according to that given function here using the if statement in Excel, as we have done many times before, giving us here, and I choose a range from 0 to 40 for the slope. So we compute the values here and get for example, for flat slope, we get this function. And when we look at the steep slope, it gives us this function. So here we have flat slope and steep slope. And then we do the same thing for the favorable and unfavorable aspect. So for the aspect, I define the function according to our given membership function here, according to these values. And then you can see here, I say, if, oh, sorry, where are we? Oh, okay, that the aspect is this one. Yeah. This if statement here, where I will say if it's less than 90, meaning if it's between north and east, then the value is 0. And then we say if the value is between 90 and 180, meaning between east and south, then we compute an ascending linear function. In the other case, we compute a descending linear function. And in the final case, when it's between west and north, the value will be 0 again. So this is our aspect. And I have done this in this table from 0 to 360, as you can see here. So it's a little bit a longer list here. Computing favorable aspect and unfavorable aspect is just the complement of favorable, meaning 1 minus the value for favorable aspect, and that gives us this function here. So favorable aspect looking like this, unfavorable aspect being the complement, which looks like that. Let's display those together again. So, and now we can go ahead with our simplified procedure. Let's start with the slope value and an aspect value. So what we do here is for every rule, we have to compute the values in the membership function for the given value for slope and aspect. So rule number 1 was flat slope and favorable aspect. So we just go with our value of slope of 10 and aspect of 180 into our table here and see that what the values are. So we have 0.5 and 1. For rule number 2, we would have 0.2 and 1. For rule number 3, it's 0.5 and 0. And for rule number 4, it's 0.2 and 0. And then we compute the minima, meaning we compute the minimum of these two values for every rule, which gives us these values. And then we have here the conclusion values, which were 1, 3, 1, and 5 for our rules. And in step 2, multiply the minimum with the conclusion value for every rule, which gives us this result here. And finally, the only thing we have to do is compute the sum of the conclusion values, the sum of the conclusion divided by the sum of the minima. So in other words, the sum of these conclusions divided by the sum of the minima. And in this particular case, it would give us this value 1.57. So if we take a different slope, if we take a steeper slope, for example, you see the value increases to 3. If we take an unfavorable aspect, let's say we take 90, the value is 5. And for any other values, if we take, let's say we take 100 degrees, which is somewhere east, southeast, we get these values and so forth. So what we can do here is, again, play with our values for slope and aspect and see what the risk will be under the assumption that we have these 4 rules. This example, we will look at this example later on in our GIS applications. So let me now go back to the slides. So this was our final example for fuzzy rules, rule-based systems, or fuzzy reasoning. And there is one exercise that you have to work on. It's the same set of rules, except that it is not, these are now not rules in the simplified way, but these are rules using the Mandani direct method. So as you can see here, the premises are the same as in our previous example. Slope is flat, aspect is favorable. But then for the risk, we have fuzzy values, meaning in the first rule, the risk would be low. In the second rule, we say the risk is moderate. In the third rule, we say again it's low. And in the fourth rule, the risk would be high. And you have here again on this part, you have the membership functions for flat and steep slope and for favorable and unfavorable aspect. And here on this right-hand side, you have the membership functions for low, moderate, and high risk. Assuming we have a range of risk values from 1 to 5, these are now the fuzzy membership functions that give you values between 0 and 1 in the range of the risk values from 1 to 5. So your task will be for your next exercise to perform this fuzzy reasoning with this example of these 4 rules with the given membership functions using Mamdani's direct method in Excel. So it should be not too complicated. If I jump back to the spreadsheet, you will have, I will make available to you the example with the cars using Mamdani's direct method, where you have more or less a template how to do it with the given premise membership functions and the conclusion membership functions, and how you can implement the 5 steps of Mamdani's direct method. You just need to modify that spreadsheet, and you have the membership functions already for the premises given here in that spreadsheet that we just discussed a few minutes ago. So that should be no major problem for you to work on that exercise. Now, before I continue with the next section of our class, I would like to ask, is there any questions? Do you have any questions with regard to the fuzzy reasoning or in general so far? If you have any questions, please, you can ask them now. You can also ask them later, of course, so you can think about it. Now, if that is at the moment not the case, then what I'm going to do is I'm moving on to the next section of our class, of our course actually, which is how do you generate fuzzy sets in GIS. And I'm going to discuss this with 2 software systems, ArcGIS and QGIS. Now, I once asked you which software, GIS software you have available. I understand that some of you had ArcGIS Pro available, others had ArcMap, and QGIS should in principle be available for everybody because it's free. May I ask you, since I forgot actually how your answers were, who has ArcGIS Pro available? You can type into the chat.
Yes, Professor. I have 3 of them.
All 3 of them. Okay.
ArcGIS Pro, ArcGIS Map, and QGIS.
Okay. Anyway, I'm going to show you most of it with both ArcGIS Pro and QGIS. Okay, Liu Wenxian, you have ArcGIS Pro or ArcMap? Okay, ArcMap. Doesn't matter because the toolbox in ArcGIS Pro and ArcMap are basically the same. So what I will show or tell you about ArcGIS Pro is very easily transferable to ArcMap because the toolboxes look more or less the same. It's not much difference. You have a catalog view as you have in ArcMap. And what you see here, when you what I did is I opened ArcGIS Pro. I created a project in ArcMap. You don't create projects, but it doesn't matter. You just create a new map, which I have here on my left-hand side. ArcGIS Pro always adds by default a world topographic map and a world hillshade as a background. Of course, you can remove it because normally we don't need it. Since I am in Europe, ArcGIS Pro opens a European view of the world because, of course, my computer knows my location. So what we have is basically like this, and on the right-hand side, what you see here is we have here our data folder with our files. So what I'm going to do is I am, for example, moving the lakes to my map, moving the parks, the rivers, and the roads. Okay, is it still working? Or what do we have? Parks, lakes, rivers. Okay. And what's still missing? The roads. And of course, our elevation model. Add to current map. So this is all now pretty messy, yeah. And as you can see, the background world topographic map, of course, has changed to the region where we have our data from, which is the part of Colorado in the United States, with the city of Boulder. Here on towards the west, you have the foothills of the Rocky Mountains. The city of Boulder itself is at an elevation of about 1,600 meters. So later when we work with that data, this information is important because if we, for example, look at a moderate elevation, in our case, a moderate elevation cannot be something around 500 meters of elevation or something, because that would be low ground, because the whole city is at 1,600 meters, and the mountains up here to the northwest, they are nearly 3,000 meters in elevation. So first of all, we have an elevation model. What we could do is we could use a different color scheme for our elevation. Let me see if I can find some suitable. Let's look at this one. I invert it so that we have from green, low elevation, to red, high elevation. So that is our elevation model. Then we would have, for example, the lakes. Okay, here you have all the polygons in it. We need to find a classification for the lakes. So what we do is, and for those who have ArcMap, you will do it in a similar way by saying we do not use a single symbol. We use for classification unique values, and when you look at the README file, you will see that the attributes we are interested in, the values are in the entity def attribute. So this is what we are interested in. And again, you can already see here, it shows us we have a covered reservoir, lake or pond reservoir, and a sewage disposal pond. So what we need is, first of all, we do not need this. We do not need all other values. I removed that also from our legend. And we, of course, we will have to, I do not use the sewage disposal ponds because we don't need them. So remains the reservoirs, covered reservoir, and the lake or pond. And what we need is, we need some suitable colors. For example, I take this one. And for the lake or pond, I take also this one. And for the reservoir, let's take this one. So what we have now is, let's for a moment take also the background away. What you see here is our lakes. Then we need the parks. For the parks, again, we need unique values. The attribute is in the entity def. So you see here, we don't need these. We don't need the all other values. Oops, I want to remove them. Remove, yeah, and then for the parks, we just use some green color. Sorry, that was the wrong one. Green color, and for the military reservation, we use some other color. So, okay, that would be our parks and the lakes. For the roads, we will have to classify the roads, and what I'm going to do here is, again, we use our unique values. As I said, for the roads, we have the attribute values in the route num attribute. And you see here we have 1, 2, 3, 4 major roads, the US 36, which is the interstate highway, and the SR, the state road 93, 7, and 119. So what we're going to do is we remove what we don't need. And for the major roads, we just use a symbol for highway. Okay, so this is now our roads, the major roads, and for the minor roads we use some, perhaps, no, that's not good enough. It's no, I need some thin line, something like that. So what I'm doing here is just preparing the map so that it looks a little bit more decent, and then we could still display the rivers if we want. Again, we would use unique values with the entity def field where we say all the other values we don't need. And this one should be some water. Yeah, anyway, I will, in the break, I'm going to recolor it. So actually now we are at the point where we could have a break. We are going to do that. So for those of you who are familiar with ArcMap, you have seen here, it is very similar what I did in ArcGIS Pro. So if you use ArcMap, you create a new map and you add data to your map using the data that I provided. And then what I'm just doing now is to make the map look a little bit nicer so that we can distinguish the features. What we have now here is basically our base map with the elevation model, or if we would, if we wish, we can add the world topographic map as a background, even with some hill shade. We can also produce a hill shade ourselves if we wish from the elevation model and use it as a backdrop to our map. So let me switch now to QGIS. In QGIS, what you would do is you would open QGIS and create a new project. And then in the same way, you will add layers. So I would add a raster layer, going to my elevation model, which is stored in TIFF format. And I would add that to our project. And in the same way, I will add other layers, vector layers. So first, let's add the lakes. Oops, where is it? Okay. Add the lakes, then we would add the parks. Then the rivers. And finally, the roads. Okay, so again, our map looks a little bit funny, so we might want to change. Sorry. We might want to change our appearance. I want to change the appearance of our elevation model. Just have to invert Oops, that was not what I meant. What I meant is to, where is it? Actually, what I wanted to do is, I wanted to invert our color scale, but for the moment, let's leave it as it is. Then, in the same way, we would have to adjust the representation, for example, of our lakes. So here we would say categorized. The value of our categories are in entity depth. Then we say classify, and you can see here already, we have here our categories. So the sewage disposal ponds I take away, the other things I leave. Just have to change the color to some blue. Okay. So this would be our lakes now. Then we go to the parks. Again, categorized. The value are in the entity depth attribute. We are only interested in our parks. So the small park, give a green color. And I leave the rest as it is. So you see here are some parks, and up in the northeast, there is this military installation. And then we have the roads. For the roads, again, we need categorized. For the roads, remember the values are in the route num attribute. And here we only need these 4 roads, and we use different colors. Let's use some color here. Okay. So what does that look like? Okay, it would look like this. One thing I would like to change is perhaps make it a little bit thicker. Let's make it, let's see, 2 points. Yeah, that looks better. So finally this one. Okay, so what we have here, and then there is just Okay, don't mind the colors now. So we have the roads, we have the parks, the lakes, and then we just could add the rivers. Sorry, categorized. The value is in the entity def attribute, and we only need we don't need the shorelines. And we need some blue color. Okay, this one. Okay, and if you want to display them, so what we have here now is we have basically the same map as we had in ArcGIS Pro. We have it now in QGIS. So you see that the data sets are pretty much suitable for both. And if you have ArcMap, you will see that it is very straightforward to do it also in ArcMap. I'm just not quite happy with my elevation model. I want to change that. Let's change it to a shade appearance. Yeah. So this is now my elevation model represented in kind of hillshade representation. And of course, what you would do is you would save your projects or save your maps or your map document in ArcMap. And then we can jump back to our slides and continue to discuss what we're going to do. So what you have now is, and if you watch again this recording, you can rebuild or you can build your projects or your maps using this data set pretty easily. So what we are going to do is I'm going to discuss the functions that you have available in these software products for generating fuzzy sets. So in ArcGIS, it is the in the spatial analyst extension. So you need a spatial analyst, and you need, of course, a license for a spatial analyst. So when I say ArcGIS, I mean ArcMap and ArcGIS Pro. It's both in the spatial analyst toolbox. And what you can do is you can use the tools from the toolbox, or you can use Python scripts and map algebra, if you are familiar with that. So in ArcGIS, it's the spatial analyst toolbox that you would use, and what you see here is the toolbox from ArcGIS Pro, but it looks pretty similar in ArcMap. You have a spatial analyst toolbox, and there you have tools, and under the overlay tools you have two of them, fuzzy membership and fuzzy overlay. So these are the tools that you would use in ArcGIS. It doesn't matter whether it's ArcGIS Pro or it's ArcMap. In both products, you have the fuzzy membership and the fuzzy overlay tools. And all these tools have parameters. So what they do is they transform a raster into a fuzzy set. Now you can have any input raster, but it has to be a raster data set. So it doesn't work on vector data sets, so it must be a raster data set, and it produces a fuzzy set, meaning the result is a raster in the same extent as your input raster, with the same cell size as the input raster, but the raster values are numbers between 0 and 1. They are membership values. And as I said, the parameters, the basic parameters are the in raster, the fuzzy function, meaning what type of membership function you want to use, and if you want to apply some hedges. You remember hedges are those modifiers like very or somewhat and things like that, where we can modify the meaning of a value of a linguistic variable. Now, this is the basic thing how it works, and fuzzy membership functions available in ArcGIS, and again, same in ArcMap and in ArcGIS Pro, is the fuzzy Gaussian, the fuzzy large, the linear, so-called MS large and MS small, near, and small. So what we are going to use most often in our examples, and what we have used so far, is the linear function. So what does it mean? How do they work, or how do they look like? Let's look at the functions in a minute, but first let's just look at the hedges that you can apply to your fuzzy memberships. You can use none, meaning there is no hedge that will be applied. There is somewhat and vary. Somewhat is the dilation operator, and vary is the concentration operator. So if you look back in our slides or in our classes when we were discussing hedges, you will see what the dilation and concentration operators mean. Usually the concentration operator is taking the square of the membership values, and the dilation operator usually is taking the square root of the membership values. So that's what you can do in ArcGIS. The fuzzy Gaussian function is defined in that way. You can see it is some resemblance to a bell-shaped probability function defined with two parameters, S, which is spread, and M, the midpoint. So you basically have in this example, you have the midpoint here, and depending how you define the spread, you get a steeper or a more dilated bell-shaped membership function. So when would you use such a membership function? You could use it when for a given midpoint or a mean value, you have a very high membership or a membership of 1, and the further away you go from that mean, the membership decreases. We had example moderate elevation. So if you have, let's say, an elevation, when we talk about this boulder area, you have an elevation of, say, let's say 1,700 meters. And the higher the elevation is, or the lower the elevation is, the more you go away from the moderate elevation. So you could use a triangular function, you could use a trapezoidal function when we talk about linear functions, or you could use a Gaussian function, or you could even use a sinusoidal function as we have defined in our class. So that's the Gaussian. The fuzzy large function is defined in that way, again with two parameters, a midpoint and a spread, where the midpoint basically is this crossover point. You recall the crossover point is that point where the membership degree is 0.5. So when we look at these examples here, where we have different different spread values. We have here 0.5 as membership value. This is the crossover point. And this is basically our midpoint where the membership function changes its slope. Yeah? So if we look at this one here, and again with the values of the spread, you can achieve different types of membership functions. If you have ArcGIS or ArcMap available, you just could read more about that parameters and what their effects are in the help, in the online or in the offline help. The linear function is defined as we have discussed in class. So it has two parameters, the minimum and the maximum value. And you can achieve both types of functions, an L-shaped and an S-shaped function, using the parameters. So if you have, for example, if the minimum is less than the maximum, then you have an S-shaped function. So if we just take a look here, let me draw something on the screen. I just want to make it a little bit different color so I can see it. Just one moment. Okay, so if this would be the minimum, this would be the maximum value, then the membership function is defined in such a way, up to the minimum, it stays 0, then it increases up to the maximum, and then it stays 1. So in our case here, the minimum value would be something like 30 on that scale here, and the maximum value is 80. So we would define for minimum 30 and for maximum 80. If we want to achieve a just want to erase all the ink on my, and if we want to achieve an L-shaped membership function, then we would define for the minimum value 80, and for the maximum value we would say 30. Then we achieve such a membership function. So whenever you make use of these tools, and you will see that in QGIS, it's basically the same. If you want, with this linear function, you can achieve L-shaped and S-shaped functions. It just depends how you enter the minimum and maximum values. So if the minimum is value, if the parameter for the value for the parameter min is less than the value for the parameter max, then you achieve an S-shaped function. If the value for the parameter min is greater than the value for the parameter max, you achieve an L-shaped function. So that's the linear. Then there is a fuzzy near, which is, I should say, similar to the Gaussian, but it is not based on the formula for a probability function. It's defined in a different way. And again, you have a midpoint and a spread where you can achieve different types of bell-shaped membership functions. So that is the fuzzy near. The fuzzy small is the, I could say, the opposite of the fuzzy large. You can see the fuzzy large achieves something like ascending membership functions, and the fuzzy small achieves something like descending membership functions. Again, with a midpoint and a spread. And then what you also have in ArcGIS, and again ArcMap and ArcGIS Pro, is the fuzzy overlay tools. There's the fuzzy overlay tool that allows you to compute intersection or union of fuzzy sets, as we have discussed it also in our course. So the parameter for the fuzzy overlay is in raster. It's basically a list of rasters that should be overlaid, and then you have overlay types. Overlay types, you can have an and, an or, a product, a sum, and which they call gamma. Now, the and or is pretty straightforward. The and would be the intersection, the or would be the union. The product is also an intersection operator. The sum is a kind of union operator, and the gamma is, I could say something you can, with gamma you can achieve things in between, but I will show you in a minute. So the and operator is defined as the minimum of the membership values, which is the simplest intersection operator that we have discussed in class. So for intersection, use the minimum. The or would be the maximum operator for the union. The product is what we also sometimes call the soft intersection, meaning the product of the membership values, which gives you an intersection operator, which is interactive. You remember we were discussing non-interactive and interactive operators. The product operator is one of the interactive operators. The sum is defined as the sum of the membership values minus the product of the membership values, which is another union operator, and the gamma is sum to the power of gamma times product to the power of 1 minus gamma. So you can achieve different operators in between. Let me see. Okay, I don't have an example here, but just assume you take gamma to be 1. Then you have the sum operator, because sum to the power of 1 times product to the power of 1 minus 1, which is 0, equal 1 here. So you have the sum operator. And if you have gamma as 0, then you have 1. Sum to the power of 0 is equal 1 times product operator. So you have, with this gamma value, you can achieve basically anything between the union using the sum operator and the intersection using the product operator. Now, these are the tools that you have available in ArcGIS and ArcMap and ArcGIS Pro. What else you have available in ArcGIS is map algebra functions. I am not, don't know if you're familiar with map algebra. Map algebra is basically a set of tools that allows you to perform all the spatial analyst functions in scripts or in command lines. So what you see here is what you can do with this map algebra functions. They basically offer you exactly the same thing as the tools in the toolbox offer you, but you are flexible, or you are free to execute these tools in Python scripts, for example. What you need to do is you need to import the spatial analyst module from ArcPy. So what I'm say now is of relevance, of course, to you who have ArcGIS and who are used to work with ArcGIS. If there is anyone among you who never used ArcGIS, so just disregard it. And then using this command, this Python command in a script will make available to you all the spatial analyst functionality in a Python script. But of course, as with the tools and the toolbox, you need a spatial analyst license. If you don't have a spatial analyst license, it will not work. And the basic map algebra operators that you can use in this map algebra is, of course, the usual arithmetic operators: division, multiplication, subtraction, or negation and addition. But there are also comparison operators like equal, not equal, greater than or equal, less than or equal, and some logical operators, the AND operator, the OR operator, the exclusive OR operator, and the NOT operator. So these are basic operators besides the tools that you have in the spatial analyst toolbox. Now, to use the map algebra in ArcGIS, ArcMap or ArcGIS Pro, you can do it using the so-called raster calculator tool. You can do it in the Python window, or you can do it in a standalone script that is written in Python, and you write it with some of the integrated development environments, for example, IDLE, or PyCharm, or any other Python environment, Python programming environment. And what you see here, this is actually the raster calculator for ArcMap. So you should be, who is using ArcMap might have used the raster calculator. Again, it's in the spatial analyst toolbox under map algebra called raster calculator. And in ArcGIS Pro, it's the same thing in the spatial analyst toolbox on the map algebra raster calculator. It just looks, the appearance is a little bit different from ArcMap, but the functionality is basically the same. Now, in the Python window, as I said, you can use the map algebra. So again, for those who are familiar with Python programming in the ArcGIS environment, so what you first would do is, of course, first of all, you would import the ArcPy module, and then you would use these commands, where the important command here is from ArcPy SA, import everything. So that would make available to you the spatial analyst functionality in your script. This is just setting a workspace. And here you see an example of using a map algebra function calculating the slope of an elevation raster that is in that workspace here. So you see slope is one of the functions of the map algebra. And what you then could do is save this result as a raster data set somewhere on your computer. So what you do is you are creating raster data sets and you are calculating results. But we are not going to discuss this here in detail. I just give you that information for those of you who might want to write standalone scripts in in Python, in ArcGIS, and by the way, you can also use Python scripts in QGIS. So what you do is you can create raster data sets. It's called casting a raster data set with the raster function. You compute some output, which is in this object here, which is called SLO for slope. And then they are, but this output is temporarily, it is not permanent. If you want to make it permanent, you will have to save it to a location in some folder. So that's the important thing. Whenever you use map algebra functions and tools, the result is not permanent, but you can make it permanent with the save method. Now, in QGIS, we have very similar situation. In QGIS, we have the raster analysis in the processing toolbox, and there we have 1, 2, 3, 4, 5, 6 tools that we can use. Again, you can see they are very similar or basically the same as we have in ArcGIS: Gaussian, large, linear, near. The power is a little bit different, and then the small. And as those of you know who are using QGIS has also other products that you can use, like GRASS or Saga. And in this Saga extension, you have also 3 tools that can be used for fuzzy sets. It's under raster calculus. There is a fuzzify tool, which allows you to create fuzzy sets. And there are overlay tools like for AND and for OR. But when you call this Saga interface and the tools there, you get a kind of a warning that says it's not fully implemented or fully tested. The tools might produce erroneous results. So let's stick to the left-hand side here, the basic functions that we have in the processing toolbox of QGIS. And again, we have here to create fuzzy sets from rasters. We have tools in the processing toolbox that transform an input raster into a fuzzy set. And the parameters are basically input raster, the parameters, and the fuzzified raster, which is the result. And again, we have here the tools, how they work in QGIS. And what you see here, the Gaussian membership is basically the same as it is defined in the ArcGIS toolbox. I have taken that information or that formula from the help functions in QGIS. So I have left the original notation. So what in ArcGIS is called M for midpoint and S for spread is in QGIS F1 and F2. And of course, you have here also all the help information that you might need. So that would be the Gaussian. The large membership is defined in the same way as it is defined in ArcGIS. Again, with spread and midpoint. The linear, again, the same thing as in ArcGIS. And again, if you look at this part here, if you can read it, it says both increasing and decreasing fuzzy sets can be modeled by swapping the high and low bound parameters. So what is called here low and high, it was called min and max in ArcGIS, and by swapping the values, again, you can achieve L-shaped and S-shaped linear membership functions. What I explained with ArcGIS is exactly the same in QGIS. And then you have the near membership function, which again is the same as it is defined in ArcGIS. The power membership function is slightly different from or is not defined in that way in ArcGIS. But what you basically see here, it is a linear. First, it's a linear function to the power of a parameter f1. So it's basically again, you can achieve increasing and decreasing using swapping the A and the B value, or the low and the high. And what you can do here is a kind of it's a kind of dilation or concentration depending on the F1 parameter here. The small membership function again is same basically for as is with ArcGIS, again with the midpoint and the spread parameter. And the raster calculator is also something available in QGIS. As you can see, it's in the raster analysis toolbox. It's called raster calculator, and it looks like that again, where you have the different functions that you can use to calculate new rasters from a given raster, or from a set of given rasters.